Hello everyone. This work introduces a novel partitioning and multi-leader election algorithm. And I'd start by dissecting the title. Let us start from the core, leader election. Well, leader election algorithms are made to select a single node in a network, the leader, usually to assign coordination or special task to it. It is used for a variety of tasks, primarily breaking symmetry network of peers, or as a building block for other algorithms that require a seed node to proceed. For instance, async where to send data collected by all devices, or find a central coordinator, or enforce a single access point. Now the second keyword here is multi. Unsurprisingly, multi-leader election happens when more than one leader is selected. Multi-leader election algorithms are used in several contexts. They are the base block upon which network overlays can get built, even on multiple scales, so overlays, or they can be local data collection hubs, or coordination for a subnetwork, and more in general, local leaders could be used to coordinate activities where the scale is in between device local and global. Multi-leader election per se doesn't say how leaders are selected. In this case, I picked them randomly, which works for some applications, of course. But in this case, for instance, all devices in the network are battery powered and at a full battery. So basically, there's no reason, besides maybe centrality in the network, to pick one over another. But what if, instead, the situation with the battery level was this one? Well, if you ask me, I'd like my leader nodes to be as stable as possible, so I would prefer those 5 with a full battery over the others. If the other nodes get charged and these discharge instead, then I would like the leader to change, maybe. Being able to express a dynamic preference over which nodes should be selected makes the algorithm priority-based. I exemplified with the battery level, but of course it may be that some nodes are static and others are mobile, or it could be that some are computationally better equipped, or with a cable versus mobile network, or better positioned in a network of peers. There are plenty of reasons why someone could prefer to select some nodes over others. Then the next keyword is self-stabilization. Self-stabilization is the ability to converge to correct states, infinite time, from arbitrary initial state. In short, you can perturb the system the way you want. If at some point its input remains stable, then the system converges. It is not a new notion. As far as I know, it was introduced by Dijkstra first in 1974. Self-stabilization is a very desirable property. And I think that is better illustrated by showing what it might happen if self-stabilization is not there. This is a non-self-stabilizing multi-leader election that we build along the road that led us to the current contribution that I'm presenting. It seemed to self-stabilize in a lot of cases, but we found this counterexample. And in this network, regardless of the stable inputs, the system oscillates. As you can see, it changes color. Imagine trying to coordinate activities within a partition that's continuously disrupted. You just can't do it. And this is why we want our algorithm to be self-stabilizing. It does not imply that this is perfect. In particular, self-stabilization tells us nothing about the duration and the quality of the transitory. But it's the necessary property that we want. The last thing that we want is a way to use the leaders. Commonly, once leaders are selected, we want to assign every device to its leader, partitioning the network. Often, the first leader are elected, and then the partition gets formed. But we'd like, if possible, to elect and partition in a single shot. Of course, there are other algorithms that do similar jobs. One is sparse spatial choice from 2014, designed for multi-leader election. It was a source of inspiration for our work, but as far as I know, it has never been formally demonstrated to be self-stabilizing. There are also other 2 works that are similar and more recent than sparse choice. One was first presented at ECAS and recently extended, and both are self-stabilizing. They use feedback loops and rely on diameter estimation. And they are conceived for single leader election, but they can be tuned to elect multiple leaders. However, we want to be able to partition the network without using operations of information collection. We want to use solely propagation, which we expect to be faster. So let me summarize our goals. We want an algorithm that can elect multiple leaders with explicit priority control and partition size. And we want to be able to use arbitrary distance metrics and no feedback loops. So information diffusion only. The core idea is actually pretty simple, but if taken trivially, it has some problems. So first, make yourself a candidate, as you know, no one initially. Then select the best leader, including information from your neighbors, if you have any. Then find the best leader and tell your neighbors. And of course, if the best leader is too far away, ignore all the information regarding it from any source and de facto create a network partition. In this network, every node is associated to its priority as a leader in the label. To simplify, we assume that at every slide, every device executes one round in which every node computes using the messages it received at the end of the previous round, and then sends messages to its neighbors. At the beginning of the computation, nodes start with no information. At the first round, knowing nothing about anyone else, they declare themselves leaders and gossip the information to their neighbors. Nodes that receive the information about the existence of a better leader join its partition. Some nodes enter an inconsistent state, here depicted with a gray filling, where they select as a leader a node that has already joined them in the partition. So it's not a leader itself. At some point, the information reaches the maximum partition size, and for simplicity, here I set 2 hops, but any valid distance method would work. Reaching the maximum partition size means that some nodes will get notified that a better leader exists in their network, but they cannot bind to it, which in turn makes them discard all the information coming from the previous network and restart the computation. And as you can see, this disrupts even the pre-existing partitions that look pretty legit. And in fact, they need to grow again. At some point, all nodes are the information of the best leader and are computing the next best of the area claimed by the first leader. Yet again, the second best leader area is limited, thus a network segmentation restart happens, which leads to another iteration, until we finally converge in 14 steps. Now, even the trivial idea has some merits, starting from the fact that it works. It also uses solely diffusion and no accumulation. It has a very succinct implementation in some frameworks. This is, for instance, how it can be implemented in Protolis, a framework for aggregate computing. The details of the code are not important. It is just to show that it can stay in a few lines of codes. But not all that glitters is gold, as the algorithm is not self-stabilizing due to the gossip not being self-stabilizing itself. And this is somewhat fixable with appropriate techniques like time replication, but they complicate the algorithm. And also we have seen with the running example, it discards information even when it is useful. We had to rebuild the second partition, the one led by node 28, that looked pretty okay up front. The trivial idea, however, is a good way to understand the contribution of this paper, which we call bounded election. In fact, in essence, the basic idea is to parallelize the computation instead of gossiping recursively, and then compete at the border instead of giving up and restarting. More in detail, every opinion on a leader is a triple, which includes the leader priority, the distance from the leader to the current node, and the leader identifier. As before, at the beginning, everyone candidates itself. Then, the best is selected among itself, and the best leader, every neighbor communicated back to us, excluding those candidacy that propose ourselves, or those whose path to the current node would be too long for the maximum partition size. The best leader that is found this way is then communicated to the neighbors. Pretty easy. Let us see it running and compare it with the trivial version. We start from the same empty network, and the first 2 steps look like the same. Indeed, the behavior is identical until the first partition gets formed. At this point, though, things change. There is no restart. The partition led by node 28 is deemed valid, and this de facto leads to a large chunk of the network that is already stable. The computation continues in the remainder of the network until the network stabilizes in 8 steps instead of 14. So bounded election pros. Well, of course, it works. And it uses diffusion only. It's got a reasonably succinct implementation, stabilizes multiple partitions at once, supports custom priorities and metrics, and we have proven it to be self-stabilizing. There's also a con, though, that is present in the recursive version too. And there are pathological cases in which the algorithm works pretty badly due to the enforced prioritization. The best idea to build one such example is to have a very high priority node that then says in and out the border of the highest priority partition. And if nodes are sufficiently inconveniently located, it may cause a continuous readjustment of the partitions network-wide. Well, I'm not going through the proof of self-stabilization in this presentation, as I can think it would get most of you sleepy, but I can explain the proof structure quickly. And the idea is to pick a demonstrably self-stabilizing fragment, known as the minimizing share, and rewrite parts of it with changes that preserve its self-stabilization. And after several rewrites, we arrive to a valid implementation of bounded election, which is in turn self-stabilizing. Now, as said, self-stabilization is super nice, it's something we want to have, but tells us nothing about the transition. There may exist self-stabilizing algorithms that are unusable in practice, as in many scenarios, as their convergence time is too long or the transient is too noisy. We thus evaluate the proposed algorithm in 3 scenarios. In a scale-free network where we switch the priorities of the leading nodes, in a scenario where there are higher priority static devices and lower priority mobile devices. And finally, a scenario where every nodes move randomly inside an arena. We are interested in how stable the partitions are. And measuring this kind of thing is not easy. We found no standard way. So we had to build a custom metric. We concocted a metric of instability. So the lesser, the better. Roughly, the idea is look behind 10 seconds, count how many times every device changed opinion about who is its leader, and divide this number by the number of times it could have changed. In the paper, it's better formalized, of course. We compare 3 algorithms. Bounded election, the trivial version of the idea, and an existing implementation of sparse choice that we selected among the others in the literature, as it's the only one that relies on propagation without recollection. So we expected this one to be faster than other proposals. For each scenario, we ran 200 repetitions of the experiment, and the whole experiment can be reproduced by anybody. The code is open source. It's implemented in Partitioning SCAFI and simulated in Alchemist. Well, on scale-free networks, we expected sparse choice and bounded election to perform similarly, with the latter having an advantage where leader nodes were more central in the network, and we expected the recursive version to be the worst. We observe instead that bounded election outperforms the other algorithms in all the conditions. We also note that, although never proven to be self-stabilizing, the classic sparse choice always stabilizes in our experiment. Changing the leader priority from the node degree to a distribution that does not consider the shape of the network has little impact on bounded election and on the classic version, but it has considerable impact on the recursive version that works even better than the classic one when the high degree nodes have higher priority. With a mixture of static and mobile nodes, we expect the ability to pick the static ones as better leaders should favor both bounded election and the recursive version over the classic sparse choice. We observe that bounded election indeed outperforms the other algorithms, and we can also observe that every some time the recursive implementation leads to disruption and readjustments of the network. So even though the classic sparse choice tend to produce a little more instability throughout the experiment, it may still be preferable if little continuous instability is better for the application than large and less predictable disruptions. With all nodes moving randomly, our expectation is that the classic sparse choice works best, as we do not enforce any meaningful priority and movements should induce disruptions pretty much continuously. We were a bit surprised when data showed that bounded election still works better. and even more surprised when the recursive version generated less instability than the classic one. So, in conclusion, we introduced an algorithm for multi-leader election and network partitioning that allows for explicit leader prioritization and arbitrary distance metrics. It is proven to self-stabilize. Data show that it performs better than the other algorithms in most scenarios. However, we know that we can build cases where the behavior is particularly bad. Although so far it seems unlikely that they occur, and we had to build them explicitly in simulation. The next steps involve more testing. We want to better pinpoint when to use bounded election and when to use something else, such as the classic first choice. We want to see how frequently the corner cases may happen, and possibly find strategy based, for instance, on dynamic changes to the priority to tackle them. We believe that bounded election is sufficiently flexible due to the possibility to arbitrarily change priorities and metrics, and self-stabilizing that it could be the building block of a new family of self-stabilizing leader election algorithms. This concludes the talk. And since my guess is that if you are watching this, I'm not there to answer questions, just please forward them to my email box. Danilo.Pianini@unibo.it. Bye-bye.